Hello folks, welcome to my channel. Today we will discuss an interesting topic, that is Venturi tube. For your information, Venturi tube is used to measure the flow rate of a fluid, and the basic appearance of Venturi tube can be seen on the screen. Now this is a pipe, and the geometry of the pipe is similar to that of a silly nozzle. This one is a differential manometer, and differential manometer is filled with mercury. Alright folks, now fluid enters the pipe with velocity v1, and as it begins to enter throat section of the pipe, the velocity of fluid increases as the cross section area decreases. Furthermore, as fluid and begins to enter the divergence section of a pipe, then the velocity of fluid start decreasing, and as the cross section area increases. For instance, assume that at section 1 the velocity of the fluid is v1, and at section 2, which is also called throat section, at that section the velocity of the fluid is v2, then v1 is greater than v2. And as I am sure all of you know that if the velocity of the fluid increases, then the pressure of the fluid decreases, since it is an incompressible fluid. So P1 is less than P2, and A1 is greater than A2, and hence D is greater than the lowercase d. Now let's use the energy equation and the continuity equation to derive an expression of volumetric flow rate, since the Venturi tube is used to measure the flow rate of a fluid. So the total pressure at section 1 is equal to static pressure at section 1, which is denoted by P1, plus dynamic pressure, which is equal to 1/2 rho, where rho is the density of the fluid, times V1 squared, where V1 is the velocity of the fluid at section 1, plus rho times G times H1, where H1 is the elevation of section 1. Now total pressure at section 2 is P2 plus 1/2 rho V2 square plus rho G H1. Now rho, where the density of the fluid remains constant as the fluid is incompressible. Now assume there is no energy loss, then the total pressure at section 1 is equal to total pressure at section 2. Therefore P1 plus 1/2 rho V1 squared plus rho G H1 is equal to P2 plus 1/2 rho V2 squared plus rho G H2. Now H1 minus H2 is approximately equal to 0. Therefore rho g h1 and rho g h2 can be neglected. So we have p1 plus 1 half rho v1 square is equal to p2 plus 1 half rho v2 square. Let's arrange this equation and move p2 towards the left side of the equation and this term 1 half rho v1 square towards the right side of the equation. So then equation becomes p1 minus p2 is equal to 1 half rho v2 square minus 1 half rho v1 square. Moreover, the volumetric flow rate remains constant, and the volumetric flow rate is defined as Q is equal to A times V, where A is the cross-sectional area of a pipe and V is the velocity of the fluid. Therefore, at section 1, Q1 is equal to A1 V1, and which is also equal to A2 V2. So we can derive the expression of V2, and V2 is equal to A1 divided by A2 times V1. So let's substitute the expression of V2 which we just derived into this equation in order to derive the expression of V1. And therefore P1 minus P2 is equal to 1 half rho where and V2 square. V2 is equal to A1 over A2 times V1 minus 1 half rho V1 square as it is. Therefore P1 minus P2 is equal to 1 half rho V1 squared times A1 divided by A2 squared minus 1. Therefore V1 squared is equal to 2 times P1 minus P2 divided by rho, which is the density of a fluid, and divided by A1 over A2 squared minus 1. Now the specific weight of a fluid is denoted by gamma, and gamma is defined as gamma is equal to rho times g, where g is the gravitational acceleration. Therefore rho can be written as gamma over g correct. So let's substitute the expression of rho into this equation. Therefore V1 squared is equal to 2 times P1 minus P2 times g over gamma divided by A1 over A2 squared minus 1. Alright folks, therefore V1 is equal to 2 times P1 minus P2 times g over gamma divided by A1 over A2 squared minus 1 to the power of plus 1/2. Alright folks, now recall that we assumed that there is no energy loss. Although we assumed that there was no energy loss, apparently there will be energy loss. So the expression of velocity which we have just derived is an ideal velocity. Now, the ratio of ideal velocity to the ratio of the actual velocity to ideal velocity is denoted by c, where and c is the discharge coefficient. So discharge coefficient c is equal to the actual velocity, which is let's denote the actual velocity by lowercase v1, and the ideal velocity is v1, the uppercase v1. Therefore, the actual velocity, which is denoted by lowercase v1, is equal to v1 times c, where c is the discharge coefficient. Now, it does beg a question of how to determine the value of c. Well, in order to determine the value of c, we need to use this chart, and it is clear that the value of c depends upon pipe Reynolds number. If now look carefully at the chart, if the Reynolds number of the fluid is greater than 2 times 10 raised to 5, then the discharge coefficient is almost constant, and that is equal to 0.984. If Reynolds number nr is greater than 2 times 10 raised to 5, then discharge coefficient c is taken to be 0.984. Since for Reynolds number greater than 2 times 10 raised to 5, the discharge coefficient remains constant, and if the Reynolds number of a fluid is less than 2 times 10 raised to 5, then we need to use this chart in order to determine the value of c. Alright folks, so finally v1, which is the actual velocity of the fluid, is equal to c times 2 times g times pressure difference between section 1 and section 2, which is p1 minus p2, divided by gamma, which is the specific weight of a fluid, divided by a1 over a2 squared minus 1 to the power of positive 1/2. Now, if we want to compute the volumetric flow rate, then we need to multiply this equation by the cross-section area. Now, the cross-section area at section 1 is A1, therefore Q is equal to A1 times C times 2 times G times P1 minus P2 over gamma over A1 over A2 whole square minus 1 to the power of 1/2. Now, this is the expression of volumetric flow rate. And remember that the volumetric flow rate remains constant throughout the pipe. Thanks for watching this video. In next video, we will solve a numerical example in order to reinforce our understanding.